Cause we all just wanna be big rock stars and live in hilltop houses driving 15 cars. The girls come easy and the drugs come cheap. We'll all stay skinny cause we just won't eat, and we'll hang out in the cool.
Here are the welding and cutting processes used in industry to create and repair products. Oxy-fuel gas welding and cutting torches, submerged arc welding, gas tungsten arc welding, gas metal arc welding, flux cord arc welding, friction welding, plasma arc welding, and many more processes. Here are some advantages of welding over other joining processes. Most welding and cutting equipment is portable. It can be taken to a construction site, a ship, or even a pipeline. Since they are portable, they can be operated inside boilers, furnaces, and a whole bunch of smaller places. Welding and cutting is way better than rivets because it is stronger, lightweight, and more complex, and just less expensive in materials overall. Here are some significant developments in the history of welding. In 1917, the strength of welded joints was first tested by the British and US governments and by Lloyd's of London, a ship insurance company. The test results proved that the welded joints were as strong as riveted joints, so then welding became an accepted practice for repair and construction. In 1918, first all-welded ship was launched. In 1920, the first all-welded building was constructed. In 1953, CO2 first used with consumable electrodes to improve the gas metal arc welding process, resulting in hotter arc, higher current, and larger diameter electrodes. In 1963, weld testing greatly enhanced after the tragic sinking of a U.S. submarine, which caused welding and brazing processes and materials to become suspect. In 1976, laser welding first used in automotive production for welding valve assemblies by General Motors. In 1991, friction stir welding processes developed in England that NASA later used the process to weld huge fuel tanks for the Space Shuttle program.
Recent developments in welding. Engineers and scientists continue to develop and improve new welding and cutting processes. New processes continue to be developed to keep up with technological advances. Some examples would be to withstand supersonic flight, intense pressures at the bottom of the ocean. Some processes can be used in zero gravity and extreme cold, like space is the prime example of how it has actually evolved. State-of-the-art welding and cutting processes keep coming out. Here are some of just a few processes out now. Plasma arc welding and cutting, electron beam welding and cutting, electroslag welding, electro-gas welding, laser beam welding and cutting, plasma spraying, electric arc spraying, flame spraying, explosion welding, friction stir welding, and exothermic cutting. Common welding and cutting processes. There are more than 100 welding and cutting processes that use a variety of energy sources, shielding gases, and equipment. The American Welding Society provides the names and abbreviations for those processes. Arc welding process is probably the widest used. The four main processes are shielded metal arc welding, SMAW, gas metal arc welding, GMAW, flux cord arc welding, which is FCAW, and gas tungsten arc welding, GTAW. All of these use electric arc. These are struck between the electrode and the base metal. The heat from the arc melts the base metal in the welding electrode or the welding rod. Oxy-fuel gas welding and cutting. Oxy-fuel gas can be used also with brazing. These use oxygen with a burning fuel gas to produce the heat to weld, braze, solder, and cut. They use gases like acetylene, hydrogen, natural gas, butane, and propane. The most used are acetylene and oxygen. They produce a flame much hotter than any other gas and oxygen mix. So the master chart of welding, joining, and allied processes.
In most common welding processes, heat and filler metal are used to create welds. Two pieces of base metal are placed together, followed by the base metal and filler metal being heated by an arc or a flame. A portion of each piece melts and forms a liquid pool or puddle of metal. As the molten filler material enters the pool, the liquids mix together and cool and becoming solid, creating a weld. Gas metal arc welding is an example of an arc welding process that uses heat and filler metal to achieve a weld. Heat is created by an arc that is struck between an electrode and base metal. In some processes, the electrode is a constantly fed wire that carries the electricity for the arc while also providing filler metal. Resistance welding is a specific group of processes that uses both heat and pressure to form a weld without the need for filler metal. In these processes, a high current passes through the base metal, and the base metal's resistance to the current flow generates the heat needed to create the weld. Resistance spot welding is a type of resistance welding where two pieces of thin metal are placed one on top of the other. Pressure is then applied through opposing electrodes while the electrodes hold the pieces together and make a connection for the electric current. The current then flows from one electrode through the base metal, then to the opposing electrode. The heat and pressure melt the metal between them, creating the weld. Materials can be welded together using pressure alone with no filler metal or heat required. One example begins with very clean pieces of metal being forced together under high amounts of pressure. The pressure used forces the atoms of the metal together, creating a weld. While heat is not added nor a part of welding with pressure alone, it may be created during the process. An example of welding with pressure is friction welding. Two round shafts can be welded together using this process with one piece being held stationary while the other piece is rotating. When the two pieces come into contact with each other, high pressure is applied to fuse them together, forming a weld. Heat is created due to friction generated between the stationary and rotated piece. They will become soft by heat but are not molten or liquid. Chemical properties determine how a material will react with other materials, while mechanical properties determine how a material reacts under applied loads and forces. Corrosion resistance and oxidation resistance are chemical properties that determine how a material will withstand the effects of the environment. Corrosion resistance is the ability of a material to withstand the effects of corrosive chemicals like acid and salt water. However, if a material is resistant to one, it doesn't mean it is resistant to the other. Oxidation resistance is the ability to resist oxidation, which occurs when oxygen combines with the metal. Strength, tensile strength, compressive strength, ductility, brittleness, toughness, and hardness are all examples of mechanical properties. They demonstrate the ability of a material to withstand loads without failing, resist pulling forces, resist pressing or crushing forces, stretch without breaking, resist fracturing, and resist indentation or scratching. Materials used in welding may have different chemical and/or mechanical properties depending on what it is being used for. Welding a metal affects its chemical and mechanical properties. While nearly all welding uses some sort of heat, heat creates stress in the metal, being an internal force within the material. It may also affect the ductility and toughness of the metal, meaning it could make it more prone to breaking while bending or cracking. A weld that is done correctly is usually stronger than the base metal, while an incorrect weld could result in serious problems. An example of this is a material that is originally resistant to corrosion from certain chemical properties may lose its resistance if the weld is done incorrectly. When heat is applied to metal, it expands or increases in size. When heat is removed as the metal cools, it contracts, reducing in size, both creating stress in the metal. The metal may relieve stress by warping. In general, some techniques can be used to prevent or reduce movement and stress during welding, like tacking the pieces together, using welding jigs or fixtures to clamp the pieces, preheating the parts, heat treating the parts, and use the proper welding procedure.
There are various different processes that are used to achieve different purposes. General post-weld processes include annealing, stress relieving, and quenching and tempering. Heat treating also can be applied before and during your welding process. This includes interpass heating and preheating. Even though they are performed at different stages of the weld process, they still serve a common purpose of reducing stress. Preheating is to raise the temperature of a material before welding, preventing expansion of a part. Interpass heating is the heating of a metal during the welding process or between passes. It is used for thicker material to maintain a high temperature during the welding process. The high temperature is to prevent the material from expanding or contracting. The annealing process allows the material to be heated and cooled slowly. It consists of heating the material to a suitable temperature, holding it there for a certain amount of time, and slowly cooling it in the furnace. Stress relieving, similar to annealing, is allowed to be heated and then cooled slowly, except at lower temperatures. It is heated, then kept at the same temperature to release stress for a couple hours, and then afterwards allowed to cool to room temperature. Quenching and tempering is performed after the weld is complete. This process is to harden alloy steels. The material is heated for a certain amount of time, then cooled quickly by submerging it into a water bath. The relationship between voltage and current. Voltage is the force that causes electrons to flow in the circuit, whereas current is the flow of electrons in an electrical circuit. Unlike current, voltage is always present in a circuit. Current, when it is in the circuit, is closed, doesn't exist until voltage is allowed to flow and forces electrons across the circuit. There are two measurement systems commonly used in the industry. US customary is what we use in America as well, and then European is SI metric. It is important to understand the system that you use for your own safety and the project material that you are making. For example, gauges on an oxy-fuel torch reads PSI and not KPA. In order to ensure that you are using the proper measurements, you need to know both to run your torch well. Also, before you get to welding or cutting, you need your material. The difference between inches and centimeters and larger feet and meters is a big difference. Understanding what measurement to use has a big impact on the resulting length of the material, which can totally throw off your project.
Hey, what's that measurement we needed at? 3 feet? Okay. I'm holding my tape in my left hand because I've got a mark with my right hand. So let's see here. You said 3 feet, right? Oh, that's not 3 feet? Oh, I should be using my imperial tape measure. That's always on inches. Both sides are inches. So then doesn't matter which side, whether I'm holding with my left hand and marking off the top of the tape or holding with my right hand and marking off the bottom of my tape, 3 feet is 3 feet. Woohoo!
I touched it and my mind went. What am I doing? I don't know what to do. What are you guys doing?
All I see.
Most welding and cutting. Oh shit.
Holy fuck. That one's done.
Wait. Oh, I fucked that up. That was so bad. Hang on, I definitely fucking typoed there.
Here are just a few of the processes out now that have recently come up. Fuck.
I'm the welder. I cut the metal, I weld the metal.
Done. Was that bad?